Welcome to EDU World Space.
In this question, we've got a thin uniform rod that has a length L and a mass m, and we are to calculate the magnitude of the gravitational force that the rod exerts on a particle with mass m that is on the axis of the rod a distance x away. And then we are to show that this result reduces to the expected result when x is much larger than L. So first of all, let's start off with a little picture. So we've got a rod of length L, and we want to be able to calculate the force on a mass m that is sitting over here. It is located a distance x from one end of the rod. And what we're going to do is follow a very similar approach that you can apply to a lot of questions like this, which is we're going to take a look at just a little piece, an infinitesimally small piece of this rod. We're going to call it dl. And we're going to calculate the force from just that little piece of the rod on m. Once we do that, then we can just integrate over the entire rod in order to get the total force on the mass. Okay, so we know that the force between m and this little element dl is going to be gm times whatever little piece of the total mass is included in dl divided by the separation squared. So the separation between m and dl is going to be x plus l, where L is just this little part between, it's the length between the end of the rod and this element dl. So this is a formula for df. In order to be able to integrate this formula, we do need to get it in terms of one variable, because right now we have two variables, m and l. So what we can do is we can change dm into the linear density of the rod times dl. So basically this formula is just a density times a distance that's going to give the amount of mass that's contained in the little piece dl. So once we do that, make that substitution, that's very good because now we have everything in terms of L and we can do our integration. Okay, everything else in the formula is a constant. So let's go ahead and do the integration. So the total force is going to be the integral of df, all the df's, from 0 to L. So remember that we're integrating over L. So L is going to start at 0 and it's going to go to the complete length of the rod, capital L. So then I am going to just substitute in my expression that I found for df. And just to make everything a bit more clear, I'm just going to take the g lambda out because that's all a constant and we can just focus on the part with the variable for the integral. So this is actually a fairly easy integral. Even though we do have that extra x inside, it doesn't matter too much. The x is just a constant, of course. So the integral or the antiderivative of that is going to be minus x plus L. And if you don't see y, then just take the derivative, make sure you get the original expression. And you do need to use the chain rule for that. And we're going to apply that from 0 to L. So here we go. I'm just going to move this over a little bit so I have room. So first I'm going to sub in L. So this is going to be 1 over x plus L, negative of course, and then minus, so it becomes a plus 1 over x. Okay, x is not the variable, right? X is a constant. Just to remind you, those L's we're subbing in for the those boundary conditions we're subbing in for little l. So we can easily combine this into one expression by making a common denominator. So the first term here, I'm going to multiply the top and the bottom by x. And then the second term, x plus L. So that makes it so that the denominator of the entire piece is x times x plus L. And then we get negative x plus x plus L on the top. And that's kind of good because the x's cancel. So things are getting a lot simpler. And so in total, we get gm lambda L over x plus L. We can simplify this even more by noticing that lambda times L is just the mass, right? So the density, linear density times the length is just going to give the total mass of the rod. So we've got G little m, big M is the mass of the rod, x plus x times x plus L on the bottom. So this is a final expression for the force from the rod on this little mass M. And then the last part of the question asks us to show that the result reduces to the expected result when x is much larger than L. So basically, the expected result is that if x is much larger than L, then the rod basically looks like a point mass, right? So you're basically looking at the rod from very far away. It does have some length to it, but it's just going to look like a point mass essentially from a far distance. And so what we expect is to get GMM over x squared, right? That would just be the force between two masses a distance x apart. So let's think about that. So when x is much larger than L, what's going to happen to our formula? Well, if you take a look at the part that has the x plus L, and you think about that, if x is much larger than L, then adding L to x doesn't really make a big difference. And so we can just approximate x plus L as just x. Okay, so what do you get? In that case, we get GMM x times x. And so we do get that expected result, GMM over x squared. Okay. So that is the final answer.